So anyway, if I'm getting outside your comfort zone, absolutely just interrupt me, because I'm going to try to give like a sort of a brief introduction at the start into the whole area of many-body localization, which, if you haven't heard, has sort of been this ballooning topic the last 10 or 15 years that it's become a thing. And so anyway, I'll give a sort of introduction into that, and then, well, here's my outline. I'm going to talk a little bit about my proof, my somewhat slightly incomplete proof of the existence of many-body localization in one dimension. And then I'll get into this issue of the discontents, the challenges. There's a few people who are just not sure that there really is such a thing as a true transition. And then after I finish debunking all those people, then I'll get to back to this normalization group picture, strong disorder normalization group picture, which is a way of trying to understand what the transition is like now that we are hopefully convinced that there is such a thing. And well, okay, we'll get to these phenomena, and in the end, I'll get very specific approximate flow equations that look similar but not exactly the same as the Kosterlitz-Thouless flow equations that celebrate KT transition. Anyway, so let me get started. We're talking about many-body quantum systems. So we have the localization, which traditionally you think of as, Anderson localization, a single electron, a single particle moving through a disordered medium. Then it sort of gets stuck in one place. Well, one sort of slightly novel way of thinking of that is that you have like a conservation law, if you will, which is the position, and the eigenstates of the system basically are in one-to-one correspondence with the positions that the particle might be when it gets stuck. And but when we go to a many-body quantum system, then we have either a spin or a collection of particles. There are obviously many more quantum states involved. Instead of you have a box of size L, and then instead of L states or L positions, you have 2 to the L spin configurations or particle arrangements. And the whole idea behind many-body localization is that disorder is strong enough, essentially everything gets frozen, and you have essentially, if it's a spin system, the spins at each of those sites are kind of like independent conserved quantities. Well, then, of course, the spins aren't exactly conserved quantities. They don't commute with the Hamiltonian, but you can perform a rotation, maybe not a very big rotation, and basically transform the spin operators into what are called lyons, or local integrals of motion. These do actually commute the Hamiltonian, and so then these modified spin operators remain time independent. The system is then frozen. There's no transport. So that's the phenomenon of many-body localization. How do we manifest it? We see there's no transport. It's a kind of localization and configuration space. For example, if you look at wave functions, they would be supported on less than the full space. In terms of entanglement measures, you have area law rather than volume. Violation of ETH. ETH is kind of like the polar opposite of MBL, which is ETH is short for eigenstate thermalization hypothesis, which is sort of the quantum version of thermalization of approach to equilibrium. It's maybe a little bit stronger than that, but let's just think of it as far as we're concerned here is a statement that the system has a way of relaxing to equilibrium. Since an eigenstate, it was basically saying that individual eigenstates actually already show signs of this thermal ensemble, if you will, in individual eigenstates, which is a very strong statement. Well, let's think of it as being a measure of thermalization. So if you think about even just ordinary Anderson model localization, a particle stuck in one position, well, then it's not thermalizing, right? A thermalized particle would be diffusing around your space. And same way when you apply like thermalization in an MBL system, you have maybe a distribution of spins or energy or whatever it might be, and it's frozen, it's not thermalizing. In order to have this happen, of course, the system has to be isolated. As I'm sure you know, when you have a quantum system, it's in a pure state, but if it interacts with an environment, it tends to depurify the state. It becomes a delicate question of, how, and difficult experimentally, if you have a cold atom system or whatever, you have to keep these spins isolated so that they remain frozen and they don't get bits of energy coming in from the environment. In terms of level statistics, the energy levels in the Hamiltonian, under normal circumstances, that is the thermalizing circumstances, or if you think about the diffusive phase of the Anderson model, then you have random matrix statistics, so you have level propulsion. On the other hand, the prediction would be that for ManyBody localized system, you essentially just have independent spins, and so there's no reason why the eigenvalues should avoid one another, and so you would expect Poisson statistics. So Poisson to random matrix statistics is one of the key measures that people do. There's a lot of numerics that are done in these systems, and this is one of the key measures you look at to try to discern if you're transiting from an MBL phase to an ETH phase. Then there's a logarithmic growth of entanglement for an initial product state. This is basically you start with initial product state, and then you have long range, we're going to be exponentially decaying interactions, and because of that, they dephase and they spread entanglement out, but at a very slow rate. So it's not completely frozen in the sense of entanglement, but close to that. Okay, so these are the phenomena that are very novel, especially the lack of thermalization is very novel, and we're trying to go for specific models where we believe this situation actually occurs. By the way, if we go back to some time ago, the founding paper of this field was the so-called BAA, Pascal, Leiner, Altschuler, where they proposed this kind of localization in Fock space. Sort of in the intervening years, there was kind of this resurgence of interest in NBL with focus on this idea of basically integrable system point of view. And so that's kind of like the modern way of looking at it. But the field really goes back quite a way. Anyway, so here's a specific model, which is the model that I actually looked at in this big paper from, I guess it was 2016 paper, proving the existence of, in one dimension, of an MBL phase modulo some assumption on level statistics, which I'll get into in a bit. But basically what we have here is an Ising situation. You have the magnetic field, and then we have the nearest neighbor interaction here. Most of this is Hamiltonian is diagonal in the Z basis, but then we have this one bit which is off diagonal here. So this I think of as an interaction term, even though it's a single particle operator, simply because if this were absent, then the Hamiltonian would be diagonal. There'd be nothing to do. So if we perturb with respect to this operator, we start to see the interactions between the spins. So this simple, the Hilbert space. And so as far as my work is concerned, I just wanted to take the simplest possible situation. So I kind of made things as easy as possible for myself. I made all three of these coefficients random, but this one's small. And with nice probability densities. Anyway, so I can just see what I can do with that. As I mentioned in my introduction, MBL system, if it's fully ManyBody localized, it would have a complete set of conserved quantities. Well, that actually is sort of a content-free statement unless you say something about what those conserved. Of course, each eigenstate of the Hamiltonian is in some sense conserved quantity because it's time independent. But we want these to be quasi-local, so that what that means is in order to define these local integrals of motion, you perform some kind of a basis change on the Hamiltonian, and this basis change should be close to the identity in some reasonable sense. It has some kind of exponential tail to it. So can we construct these quasi-local integrals of motions? Well, we wanted to find this unitary that diagonalizes the Hamiltonian. But this is actually kind of an interesting thing because when I was first, David Hughes kind of got me interested in this problem. And it's like, well, what we're talking about is basically, we're trying to do like a tensor product approximation. We want this, the Hamiltonian to be something approximately a tensor product. But somehow I couldn't directly answer that question. Instead, I had to just go ahead and diagonalize the Hamiltonian. Once it's diagonal, then yeah, it's a tensor product. Anyway, so I'm trying to find a unitary that diagonalizes the Hamiltonian. It's a tall order. If this U then diagonalizes H, what does quasi-locality mean? The effective U on a set of spins that span a distance L in the lattice should be identity plus exponentially small in L. That's not the end of it though, because you might have some rare non-percolating regions where this property fails. You're always going to have some large rotations. You know, even though you have all the spins throughout, maybe are completely frozen or almost completely frozen. Since we have random couplings, there's always going to be some where the system looks. Normally, I'm thinking of a weak interaction problem, but it may be some isolated region where it's strong interactions. And then you would expect those spins to thermalize amongst themselves. And then if you're going to diagonalize the Hamiltonian, you would need a large rotation. So, as I said, there's going to be large non-percolating. Of course, in one dimension, you don't think of anything as percolation, but actually we have this sort of long-range percolation model that comes up, and in that sense, it makes sense to talk about non-percolating regions in one dimensions. And then this property, we're going to relax this idea that it has to be close to the identity matrix on those resonant regions, as we call them. All right, anyway, so if you have the U, then you can just perform the rotation on the spin operators, and then it's just a tautology that the Hamiltonian commutes with the tau variables, also which are colloquially called the L bits, localized bits. So these actually commute with the Hamiltonian, so they remain localized for all time. Okay, so I don't know why the bottom of this is cut off, but that's just the projector. Anyway, apologies to Hughes, Nandeskar, and Oganessian. Okay. So anyway, just let's go back to basis, what are we talking about? We have a tensor product of a whole bunch of spins like this on a line. And actually, if you reduce this Hamiltonian to a single spin, this is what you get. You have a magnetic field on diagonal, H minus H, and you have a flipping term, which is small gamma off diagonal. And in this one spin case, clearly, if the flipping term is much smaller than the magnetic field, then the eigenfunctions are going to be close to these, L bits, if you will, 1, 0, and 0, 1. So then the eigenfunctions resemble the basis vectors. And in fact, you can use the basis vectors to label the eigenfunctions, right? So that becomes really our L bits. There's going to be an L bit which is close to 1, 0, and an L bit which is close to 0, 1. It has a little bit, it's not going to be exactly 0 anymore. It'll be some more gamma piece here, but it still closely resembles the basis vector. On the other hand, if the magnetic fields are very small, then the eigenfunctions are close to 1, 0, 0, 1. Well, 1, 1, 1 minus 1. And so this is basically hybridization. So you have virtually complete hybridization. There's no real way to associate those with the basis vectors here. So basically, in order to show that you have NBL, we have to show that this circumstance is predominant throughout the space, and this circumstance is rare. Any questions? Okay, good. Or bad, whatever. Okay, so now how do you go about constructing this local intervals of motion? Well, in that single spin case, it's pretty clear. You just diagonalize a 2 by 2 matrix, but there's sort of this problem where in the rare regions where the perturbation theory breaks down, they could potentially infect the rest of the world, so to speak, and spoil this idea of basis vectors being close, bearing a close resemblance to the true eigenstates.
What's the technical meaning of breakdown here?
Well, that would mean, I'll get into that. That's very, that's a leading question, but I think in the next slide or two, I'm going to give very specific criteria for what it means to break down. So let me defer that for a second. So anyway, as I mentioned, I'm going to talk, hopefully not too long, but about my proof, because it is a long paper and it's somewhat technical in many respects. But one of the things it's actually proved to be quite important to have a non-perturbative proof, because there's been people have questioned that you don't really see this NBL phase very well. At least the phase transition you don't see very well numerically, and so some people were looking at trying to do finite size scaling and stuff, and they say, well, we don't think there is an NBL transition. Well, at least we have a solid piece of work, which isn't completely airtight, but it's close to being airtight, that there is actually an honest-to-God phase transition that's valid for infinite size systems. Unfortunately, in order to make this proof work, or even to become somewhat readable, I need to go to extremely large disorder or equivalently extremely weak interactions. Much smaller than anyone would do numerically. If you put these such tiny numbers in, of course, there are actually more extreme numbers than I even have actually explicitly cared. I don't really dare to calculate how small these numbers are, because it would probably be very discouraging. But that's kind of the way it is in my field of mathematical physics. You're just trying to show, okay, there is a transition, and the fact that it might require some coupling to be 10 to the minus 6 or even smaller, well, that's sort of beside the point. Yeah.
When you say the coupling is to be really small, you mean just some small constant value, not like decaying with system size or anything like that?
Oh, yeah. So, I mean, in this specific problem, what I have is this number gamma here. So I'm trying to perturb in this off-diagonal piece here. this is a random number, but I put a fixed number gamma in front of it. And so then I just need that to be like 10 to the minus 6 or something like that in order for the proof to work. So right at the moment, this is a purely local, interaction. We have nearest neighbor here. But what we find then is once we start doing the analysis, we get exponential tails and everything. Anyway, well, I pretty much talked about this percolation. Let me just skip that bit. So let me talk a little bit about these resonant, what I call resonant region or Griffiths regions. Those of you who have experience with disordered systems, we have quench disorder, then you know that there's this problem which was identified a long time ago, where let's say maybe you're thinking that if you have some kind of Ising model, you think you're in the high temperature phase, but you have some local region which looks like it's in a low temperature phase, or vice versa. You think on average you're in the low temperature phase, but there's a local hotspot. And so these are called Griffiths regions. And what that means is, for example, if you have like a high temperature expansion, let's say you have a very simple situation and you expect exponential decay, you have a high temperature expansion, but then that expansion is not going to work in these Griffiths regions. And then you need to make some arguments for, does that matter or not? And in fact, in disordered systems, you have these typically quite typical that you have these rare region events whose correlation functions decays with some stretched exponential or some power law or whatever. It's slow decay of rare region effects, as can be even if you're in the high temperature phase where you would expect exponential decay. So this is going to be kind of the big question really that we have to face in this NBL problem, is what to do with these resonant regions. We need to know that they're rare. So when I'm doing the perturbation theory, which I still haven't gotten to, I hope I didn't miss the slide. Anyway, I'll get to the perturbation theory soon enough. You need these buffer zones around the resonant regions because you have interactions which are decaying exponentially with this rapid decay gamma to the L. But you have a level spacing inside the resonant region, which goes like 2 to the minus R if you have a spin system. And so in order for this to be good perturbation theory, you need to have the interaction strength be much smaller than the level spacing. So otherwise you have basically resonant transitions. Perturbation theory doesn't work when you have resonance. It's like sort of like Fermi's golden rule or whatever. It's always a calculation between the matrix element that produces a transition and the energy denominator. Well, so this is the point here. So I need this L to be of order R, so that this exponential can dominate this exponential. Right, so if I just try to go to a nearest neighbor or a couple nearest neighbor, there wouldn't be enough decay to beat this very small energy denominator. So what we can do is to we can kind of expand this resonant region to include this buffer zone or collar region, and then we can do some diagonalization here, and then this sort of becomes the new basis in which we work in that region. Okay, so I guess I trimmed off the, yeah, all right, sorry, yeah. I trimmed off the perturbation theory stuff. So maybe I should say a little bit about perturbation theory over here on the blackboard. Basically, okay, let's say we have this situation here of soft diagonal on diagonal. So perturbation theory, we need to first partition. So this is going to be a H is going to be a random quantity, right? So this is going to be sites where the energy level difference HI times let's just say HI is much smaller than gamma, or HI is much bigger than gamma. All right, so then, as I said earlier with this one site problem, in this case, this is basically a non-perturbative region because the eigenstates are going to be close to 1, 1 and 1 minus 1. And in this situation where the energy difference is much larger than the off-diagonal piece, these are going to be perturbative places. Now, when we assemble all these spins, we have to look not just at the magnetic field, but also the effect because of the nearest neighbor piece that the flipping does on the overall energy level shift. And actually, that will depend, of course, on what the spins are on the neighbors. So if we have, let's say, 3 spins here in a row, there's like going to be 4 conditions, depending on what these outer spins are doing, that I'm going to have to excise the non-perturbative cases. And say that those 4 conditions might be satisfied, but it's going to be satisfied on a rare set of sites throughout the box. Because this is, they have a continuous distribution, probably that it's really close to gamma, maybe gamma to the 1/20th or something like that is going to be very small. So ultimately, then you have your space here is a line, and then you have some rare regions like this, which we think of as non-perturbative regions. The rest of space, we can actually now we have a cutoff, if you will. We have a cutoff here on energy denominators, which means that actually essentially perturbation theory is convergent. The only reason that you have problems with convergence of perturbation theory and quantum mechanics is if the energy denominator gets smaller. We excise all those cases, everything basically is convergent. We have a specific way of generating the perturbation theory using I'm talking about perturbation theory really for the rotation that we need to diagonalize the Hamiltonian. So there's these things called Schrieffer-Wolff transformations, where you basically would you define a matrix of this A, which is something like but basically it's what would come from perturbation theory. It would be delta H for gamma over delta H minus gamma over delta H. And then you exponentiate this matrix to get equals e to the A. And so you just perform the similarity transformation on the Hamiltonian. The result of which is to eliminate at least a first order in perturbation theory, these terms, these off-diagonal terms in the Hamiltonian. So anyway, it's probably best if I don't go into formulas and stuff on that. But you get the basic idea. It's, the procedure actually is pretty much Newton's method, which is to say, I use perturbation theory to determine what the ideal rotation is to first order. Form that rotation. It doesn't perfectly diagonalize the Hamiltonian, but instead of instead of having the off-diagonal terms of order gamma, now they're of order gamma squared. And then I do that again. And just like Newton's method, and the next one will be of order gamma to the fourth. You get this rapid conversion, superconvergent process, whereby the off-diagonal parts of the Hamiltonian become higher and higher order in perturbation theory. And what you find then is that, especially when you perform this exponentiation, is that you're kind of generating random walks. So a walk like this that has, let's say, it has 12 steps, that's going to be of order. The corresponding term in H and the rotated H is going to be of order gamma to the 12th. Because every step is basically corresponds to some order of perturbation theory. Anyway, so that it's a little bit technical, but it's somewhat straightforward in the sense that there's no divergence of perturbation theory. That's kind of the game in mathematical physics, what I've been playing at since I started in this field, which is, you take a typical problem, whether it be quantum field theory or the sort of system, wherever it is, your perturbation theory is usually not going to converge. But what you can do is you can maybe put some cutoffs or conditions in to make it converge, or at least you can do Taylor's theory with remainder. You can get some rigorous bounds on what's happening, and then in the rest of the, then you have to worry about the part where the cutoffs are not in place, and you have to use some probabilistic arguments to say those are rare events. For example, that's how we go to high energy. We try to show quantum field theory exists by removing the high energy cutoff. Well, how do you do that? Well, you have to show that the measure of field configurations where the Hamiltonian is extremely large, you have these infinite cutoffs, if you will, but to show the measure of field configurations where H is really large is small enough so that you can actually still integrate e to the minus H in the Euclidean framework. So anyway, so I could just kind of adapted all this stuff that I learned from working in quantum field theory to this particular problem in disordered systems. Okay, so anyway, I hope that answers your question from a couple of slides ago. Okay, so let's go on to this RG picture. So I've described it as a Newton's method, but in fact, it's also can be thought of as an RG transformation because there's a length scale which goes along with it. When we remove terms in the Hamiltonian of order gamma to the L, that means there's going to be L steps, as I described over here in my sketch of the diagrammatics, that walk can extend the distance L in physical space. So you can think of these rotations as you remove the terms in the Hamiltonian and make it to be higher and higher order in gamma. It's like you're integrating out short distance degrees of freedom. But we have to simultaneously deal with these bad regions, these resonant regions. We have to eliminate them, that is to perform a basis change, with maybe a large basis change in these regions of size L. And so there's this sort of interaction zone where you have these buffer zones that you have to worry about. Inside this buffered region, we now have what you might think of as a meta spin. Instead of a spin having two positions up and down, this meta spin, which is the degrees of freedom in this large box, takes 2 to the r plus 2L values. Well, that's a little bit strange point of view, but the fact of the matter is the interactions at this point are so small that, there's a gamma to the L, and the whole construction was designed so that gamma to the L is much smaller than 1 over this. And so even though there's a lot of these spins here, there's very little hybridization with spins elsewhere, which is what you need in order to keep moving along in the problem. So anyway, deep in the localized region, this RG has the property that the density of remaining resonant regions, that is ones that you haven't turned into meta spins yet, along with their buffer zones, they go to 0 with L. So if you think about this procedure, maybe I should draw a little picture, but there are two things that can happen. One is that the small resonant regions are in effect eliminated. And somehow with the perturbation theory is dressing things up, but the business of this problem is with these resonant regions. Okay. So we have some small ones, some large ones. If you have a resonant region like this, which is well isolated from its environment, that is, it has a good buffer zone, then we can do this large rotation, and in effect, we can erase it. Because it basically interacts with the rest of the system just as if it were just some slightly unusual spin that happened to have a large number of values to it. The remaining ones, well, what can happen with them? Well, we can wait until the length scale gets longer and longer, so the neighborhood eventually is big enough so that we could try to turn that into a meta spin. But if there happens to be another one nearby, and these end up having to get joined together because you don't have sufficient neighborhood to do what we're doing here. So this buffer zone might get polluted with another resonant region, so then you just have to combine the two. All right, so that's why I'm saying here we have these two effects. You eliminate the small resonant regions. That tends to make them go away. The goal really is to make them all eliminated. But the fattening can also make the remaining regions combine, and that increases their density. And so the proof is basically about showing that one dominates two. Deep in the weak coupling or strong sort of region, density goes to 0 in the RG. And I should mention, if I skipped over mentioning that this proof only works under an assumption on level space statistics. Basically, I have to assume something called the LLA, or limited level attraction. So this is like the main caveat. And just in words, rather than saying out the technical condition. So it says that the box of size n, the minimum level separation is no smaller than an exponential. E to the minus some constant times n. With a high probability, the probability also the probability that this fails is also exponential in n. Yeah, you always have to say, well, you're never going to get perfect. You always have to deal with the bad sets, but we just have to assume the probability of a bad set is also exponential in n. So what does this mean in terms of the systems that we know? Well, basically the systems we know well are ones with Poisson statistics, random matrix statistics. That they satisfy, so the Poisson statistics is really neutral, right? There's no level repulsion. Random matrix statistics have level repulsion. This has to do with the exponents here, this number C here. Actually, I could allow either of those cases, either random matrix or Poisson, I could even allow a small amount of level attraction, as long as you still have some kind of control on these probabilities. And that's why I call it LLA, limited level attraction. So really there aren't any systems except ones with degeneracies. This is basically ruling out degeneracies in the system, which might be produced by symmetry or whatever. You don't have degeneracies, so then what's the remaining level statistics might have a little bit of attraction, but not too much. Question?
Is the upshot of this proof that the strong disorder RG methods are correct and valid, or is this proof a little bit bigger than that?
Well, I guess depends on what you mean by strong disorder RG.
This kind of implies that what I'm able to do is like integrate out all of these regions where the disorder is particularly particularly strong, which is kind of this idea of the strong disorder RG.
Yeah, exactly. Yeah, I mean, I would say this justifies strong disorder RG with the caveat that we're only justifying it in this rigorous sense in the strong disorder region, whereas I'm going to get to, we're going to try to apply strong disorder RG also to the transition zone. So in that case, we just sort of have to say, well, that's going to be the assumption that that this picture of bad regions separated by thermalized regions, that this is a good coarse-grained description of the problem.
So this is kind of justifying strong disorder RG, but only the weak disorder limit.
No, this is a strong disorder limit.
But you were saying something about the gamma fluctuation from very, very small.
Yeah, so the gamma, so we have disorder, I mean, yeah, so you have the Hamiltonian is, it's going to be diagonal plus gamma times off diagonal. So this is going to be a small number, but of course you can turn it around like this, sure, and then it would be large disorder, because all the disorder would be multiplied by 1 over gamma. So I use those terms interchangeably.
Sure.
Yeah, okay.
Sorry, could you explain why you did the limit in level attraction?
Basically, well, I guess the main issue here is with these resonant regions where I don't have much control over what's going on, but nevertheless, I need to control its interaction with the rest of the world. And so I have to say, well, okay, I don't really know too much about this, but I know that the matrix element is small. What do I do about the energy denominator? So then I need some statistical control over the energy denominator.
It's that 2 to the minus r that you control.
Yeah, right. See, here I just said typical delta E is 2 to the minus r. Well, what if you have an atypical one? Then I need to know how likely is it. I need to know that the probability of having an atypical delta E is also an exponential in R. Yeah, it's a very good question. Yeah. Okay, so now I want to talk a little bit about avalanches. So basically this, what I've described so far is kind of what went into my proof, but now we can sort of look at this from another point of view. What happens if we consider flip rates for off-diagonal matrix elements which connect resonant regions with spins outside the buffer zone? Well, see, this is exactly what I considered here. Right? This interaction goes like gamma to the L. But if I'm going to go like toward the transition, then this gamma, is going to start to grow. It's no longer 10 to the minus 6. It might be something a little bit stronger. So there's going to be some decay length for the interactions that go a distance L. And let me just write this, try to kind of like choose my units in the exponent here as 2 to the minus 2L over zeta. So that means zeta is a decay length in a certain system of units. This is for the matrix elements connecting the resonant region to the rest of the world. All right, so now we need, this is something we need to be small compared to the level spacing, which I'm still going to say is 2 to the minus r plus 2L. And so then we see that this decay rate of the zeta inverse has to be bigger than 1. In fact, we can define the deficit here, the difference between zeta inverse and 1, to be the excess decay rate. As long as x is positive, then this rate of decay is going to beat this rate of shrinkage of the energy denominators. So this goes back to the people that I've cited down at the bottom of this slide, De Roque and Huveniers and Theory. They introduced this. They said, heuristically, wait a minute, you know, there's this very special phenomenon going on, which seems to work out in one dimension, but you see, this is going to be everything's going to work out a little bit differently in higher dimensions because level spacings then are not going to go as r, but r squared, let's say in 2 dimensions. So this is going to have kind of a perturbative effect, which can have drastic implications for the existence of an MBL phase. And I just kind of blithely ran over this because I just said, okay, well, I'm going to assume one exponential is much bigger than the other. No problem. But now we're going to be talking about transition. This is actually maybe, in fact, I would argue that these effects, the so-called avalanche effects, are going to actually be the most important effects that govern the transition. The reason for the word avalanche, it's a bit of a misnomer, but you see the size of this buffer zone, if gamma is increasing up to, you know, the critical rate, then we need to make this buffer zone larger and larger in order that, because we kind of, you start in a hole here because you, at the very beginning, even if L is 1, we have this 2 to the minus r to be. So then some multiple of r is necessary in order to get a good buffer zone. But that multiple gets bigger and bigger the closer we get to the to this critical decay rate. So as x goes to 0, the size of the buffer zones get bigger and bigger. What does that mean physically? It means that you have a bad region. It can thermalize its neighboring spins, but then those neighboring spins join the bath, and the level spacing goes down. So then that means you have to go even farther in order to get that condition that the transitions are smaller than the level spacing. And it's kind of a snowball effect or avalanche effect. Of course, physically, in order to engage in processes that involve these exponentially small matrix elements, you're going to need enormous time scale in order for these processes to actually move. So it's an avalanche, but it proceeds like in physical time extremely slowly. It's very difficult to see numerically. That's a bit of a challenge, which we'll get to in a minute. Okay, so then we just now take a little bit of a sidebar here to talk about the people challenging this sort of standard picture of NBL in one dimension.
John, how much longer? We're around 10 minutes. Can you...
Yeah, I'll try to squeeze it in there yet. There was this early work with showing a safe scaling collapse when you take the disorder going of size L. So that means, according to them, any fixed disorder strength would thermalize for sufficiently large box size. But by the way, L now is the box size, not the distance from what I was using in the previous slides. But then this group of people, Abanin, Kamani, Gopalakrishnan, Bowman, Porter, Durbin, Vassar brought the big guns and they shot this down and saying, or at least disputed this conclusion, showing that some drift of L is expected, but you actually see this even in systems that are no-gap transition. Furthermore, if this were really the case that the critical disorder scaled up with L, or even with some smaller power of L or something like that, then eventually for large enough L, you'd be in the regime covered by my proof. Where, at least if you believe my proof, then there, you know that there's NPL. So this scaling maybe is some kind of addition situation, but it's not going to be, it can't go on forever. And they're saying, yeah, there really is a transition. More recently, there was further arguments by Sells and Pokovnikov. Pokovnikov is, I guess I spelled his name wrong, but anyway, he's one of the main discontents, if you will. But again, these alternative views don't take into account that the system sizes studied are insufficient to see the predicted phenomena, particularly the avalanches. In the avalanche picture, there are these rare events. So almost by definition, they're hard to see if you have a specific, you try to run through maybe 1,000 disorder configurations, but if they're really rare events, chances of seeing them are still going to be very small. Anyway, so this is really hard to see in the numerics, but anyway, furthermore, what really seems to be the case is that for modest system sizes, you're only really looking at crossover phenomena. You need much larger system sizes, too hard to be done on the computer. There is sort of a way of getting partially around this, which was more recent work, Morningstar et al., Kamani, Huse, and Loix, and Omnes. Basically look at the avalanche susceptibility. So it's almost like, okay, you've got an avalanche here. It's like this tilted snowfield. And like you can do a little probe in there, take your shovel and say, oh man, there's a layer in there. It's ready to go, without actually setting off the avalanche. So they did some numerics on that and showed that even in a finite, relatively modest L, you can see this avalanche readiness persist to quite a bit stronger disorder. And so the conclusion is that the L equals infinity transition is going to be quite far from the regime studied in numerics. And you shouldn't assume the drift of the apparent transition continues forever, because eventually you'll get into the regime covered by my proof. Okay, so anyway, so that's the end of that little sidebar. So now let me just take a few moments at the end of the talk to talk about the strong disorder RG. I think we've more or less discussed this whole issue of L blocks and T blocks. T blocks are the thermal regions where which are localized, so those are the intervals between those bad regions. Sorry, the T blocks are the thermal regions, which are the bad regions. The L blocks are the places where the quasi-local basis change have been defined. So at least deep in the MBL region, these T blocks are rare. Occasionally they join up, but most of the time they're just disappearing from the system as you run the RG. The RG involves integrating out, if you will, or just taking all those T blocks of length between lambda and lambda plus D lambda, either erasing them if they're isolated, or if they're not, then they pair up with the neighboring T block. So these are the two mechanisms which I talked about. The new thing, though, is that I haven't mentioned already, is that this avalanche parameter, X, this deficit decay rate or excess decay rate, which we need to be positive, in order to stop the avalanches from consuming the entire system. This has a tendency to flow downward with the RG because when you erase the T blocks from the system, they interrupt the decay of interactions. So this is an important phenomenon, which Jerome calls a rule of vaulted decay. But basically, you have some exponential which goes down, and then you get a T block. It's kind of like a short circuit. There's zero resistance here, so that there's no decay through there. And then the exponential decay continues once you pass through it. So you can see that the density of T blocks has the effect of reducing the overall exponential decay rate if we measure it with respect to actual distance. So that means this X is going downward, and this kind of completes the picture in the strong disorder RG. So it was kind of interesting that I came up with a very simple two-parameter model that would incorporate these effects. And just before the pandemic hit, I went and visited David Huse and Ellen Morningstar, and they had been working on this functional RG, which incorporates the strong disorder RG. And so then we like, okay, can we reconcile these two things? You know, it's a fairly complicated thing. We've got this rate, R lambda val, which is basically the density in a given cutoff of T blocks with a given size L. How does that flow as you raise the cutoff? And this is a complicated equation. We were able to reconcile these two pictures by extracting from this key parameters, which will end up being the KT parameters X and Y. We've already seen the X, which is sort of the usual horizontal axis in the KT picture. This Y variable, this rate here actually has dimensions 1 over length squared. So if we scale it up, we get a dimensionless notion of density of T blocks at a given scale. And the phase transition will be governed by the point where both the density and the deficit are vanish, and the fixed line of the transition, which is at y equals 0, it becomes unstable for negative value of x because of the avalanche effect. All right, so then we make some arguments about the most likely way of forming pairs, pairing up of these T blocks, and get a recursion relation, which says that when we go to the next scale, which is lambda over x, the rate is the square of the previous one. Because you have two densities, things have to combine. And so you get a squaring operation. In terms of the dimensionless parameter, we have y lambda over x ends up being y lambda over x lambda squared. So this is the basically the recursion relation. We have this flow equation for the rate, the xdt equals minus y, and we have this recursion relation for the density. And actually, these two things all by themselves determine the nature of the transition itself. You can see the separatrix of this flow is the curve y equals x squared, because if you plug into this y equals x to the 2 plus delta, square it, divide it out, you end up with y equals x to the 2 plus 2 delta. So you have this exponential departure from the separatrix, which is this parabola. Once you have that, you can compute the flow along the separatrix by just using the most simplest ODE. And you're off and running. You can then compute the way that the diverging length, which is the point at which the orbit departs the vicinity of the separatrix, and we get this unusual form for the divergence. From an initial displacement delta 0, you get this log-log form for the exponent for the divergence. So this is going faster than any power of delta 0. So in effect, we have correlation length exponent nu equals infinity. Now in the KT, you have a very similar, flow picture, right? You've got something like this. You get this fixed line here. You have X and Y. You have separatrix, and we have a flow down here and a flow like this. But when you compute the divergence of the length scale in KT, you get this exponential of a power. So that's a very strong divergence. It's somewhat weaker, but it's still nu equals to infinity. Okay, so just almost done here. I just want to show these nice pictures. You can devise an equivalent continuous flow. We don't have to use the discrete flow. This is equivalent in all respects. You'll notice that this flow has this non-analytic piece here, which kind of threw off some of the early people. There were a couple of papers who, Serbin and Vasseur and some others, who were predicting that this transition was in the KT universality class. But if you assume analyticity, then this would just be like YX or something like that, which is what you have in KT. But what we see here is that the squaring operation means that you kind of really have to take logarithms of the variables in order to, in effect, linearize the problem. And so this appearance of these logarithms puts you outside of the usual KT universality class. Anyway, this is kind of the picture here of the separatrix that we see by running this flow equation. So there are a lot of parallels with the KT transition, which are really amusing to think about. Even though we're not in exactly the same universality class, topologically the flow looks very similar. These T blocks are kind of like the vortices, they're non-perturbative effects. And their tendency to grow or shrink determines what phase you end up with from any initial starting point in the diagram. In KT, you have vortex binding. So that's analogous to the binding of the T blocks that we saw. But when they bind, in our case, the vortices normalize the stiffness. In KT, it normalizes the systems and stiffness and actually makes it weaker, it screens. But in our case, the T blocks normalize the decay rate, that rule of halted decay, and it actually accelerates the process of going toward the transition. So that you can think of that as anti-screening. Okay, I think that's my last slide. Thanks for your attention.
Okay, well, we had some questions during the talk. Are there any more?
Yeah, the screening is a flattening of the exponential that you do for.
Exactly, yeah.
That's a consequence of excising the T block, right?
Yeah, right.
So I can see this as either I literally take off this block and I attach the system on the two.
Yeah.
One used to be off, or I view this as a longer interaction, which makes this parameter X lower values.
Yeah, I mean that's exactly right. I mean, but the way I like to think about it is, you could say you have exponential decay, but in an unusual metric where all these blocks are contracted to a point. And in fact, in my proof, one of the key lemmas is to show that this new metric is equivalent to the old one up to a factor of 10 or whatever. The problem is that these volumetric effects, which I pointed out to in this early slide here, this volumetric effect here is with respect to the true distance, not the weird metric. And so that's why you really need to relate to the true distance, because once you put in these short circuits, it makes it harder to absorb resonant regions in subsequent steps. So it really does accelerate the process of going into thermalization pretty dramatically. Yeah.
I don't think I followed the RG bit very closely, but I want to understand the relation between this and the proof, which is presumably the strong disorder limit of the RG.
Right. Yeah.
So the proof is in the strong disorder and dilute thermalizing movements limit of the RG. Is that right?
Strong disorder. Yeah. I'm not sure what you mean by dilute, but
So where on the X and the Y axis?
oh yeah. So so if my proof, so to speak, is way over here. Okay. Tends to be so yeah, basically in this region.
Right. And so if that region is the rigorous version of that flow, can you say exactly what the RG time is?
Okay, so yeah, RG time. So it's a discrete RG because we're letting the length scale basically go up by a factor of 2 at each step. And for technical regions, it goes up by a factor of I don't know, slightly less than 2, but anyway. So it's a discrete RG going up with a factor of 2 with each step. And that corresponds to moving along these curves like this.
So what's the procedure in your proof that corresponds to integrating stuff up at once?
A short distance is short. I think I mentioned this. When you do these rotations, there's some perturbative rotations that are used to bring the Hamiltonian locally in much more closely towards to being diagonal. So that's in the perturbative regions, and then you have the non-perturbative regions. If they're well isolated, then I do a large rotation to diagonalize them. And so once we put them into diagonal form, modulo remaining matrix elements to faraway places, I think of that as having been integrated out.
So is your proof? And one, is there only your statement about consistency between your proof and the RG trajectory?
About the inconsistency?
No, consistency between. Yeah, if I try to embed your proof as a trajectory along this RG.
Yeah.
Can I have some information about the exponents? Or no?
Well, yeah, no, it's I mean, so if you're just talking about the proof, that's stuck way over here. Okay, so it's when you're talking about exponents, you have to go over here in the vicinity of the transition point. So yeah, so basically my proof is just simply to establish that there is an MBL phase, and presumably, of course, we don't know rigorously that there's an ETH phase, but we do what we can. And we assume there is an ETH phase, and then if I establish an MBL phase, that must be a transition. The nature of the transition, well, okay, now we go deep into heuristics, and that's what the second half of my talk was about. Yeah.
So physically, what these previous RGs that got a KT transition, what they were missing was this kind of all-in decay effect of interactions. Is that correct?
Well, yeah, the previous RGs were, they actually, some of the earlier ones were rather clumsy. They didn't actually, there was actually symmetric under replacement of T blocks or interchange of T blocks and I blocks. I think once you put in something in the rules, they were kind of, feeling away in the dark for what the rules should be for these RGs. And eventually, you got to input this halted decay business, and then started to make a little bit more sense. And ultimately, it just was fortunate that the latest version with David and Alan was ready just at the time when I was playing around with these 2-parameter recursion flows. And we got together and it turned out you could actually derive these flows from their updated version of the RG.
I guess my question is, you think that those RGs that said that the transition is KT, those are just wrong and you can point out sort of what they're missing?
Yeah, I mean, I think that, you know, it wasn't, these papers were really short. I mean, they just sort of said, you know, this, we have these effects, and then they made a natural assumption that the flow equations would be analytic, right? Once you say it's analytic, well, then it's KT. Because you have these 2-parameter flows, expand them, the terms on the right-hand side are, you know, second order, then there's only, you know, it's only one thing you can write down. So as it turns out that, you know, since you're descending from a functional RG, there's no reason why it necessarily needs to be analytic. As it turns out, it's not.
Question from Vedika on that.
Okay.
Yeah, John, have you tried doing your proof for flow case systems? Would anything change substantially?
I haven't tried flow case systems, but I would assume that things would go along more or less the same way.
Okay.
Okay.
Yeah.
One thing I'm a bit confused about is your proof seems almost inevitable. How do I, and you said that, like, of course it's a proof, so it is inevitable, but at some point you have to do some calculation to show, okay, in this region, thing is justified. Maybe I just missed it in your talk. So how do I know that when I do these rotations, the off-diagonal terms do get smaller? It's like, what is the kind of outline of that sketch?
Yeah. Well, you know, there's a lot of subtleties in the proof, and we had a kind of a group meeting on Friday where I went into some more details, but yeah, I sort of, you know, yeah, it's not easy. It's like 60 pages long. I guess the challenge is that like if you do a single step, it's pretty straightforward, as I indicated, that you can just put in some cutoffs on the denominators, and then the perturbation theory converges. So you know that you can do it to first order, and then the remainders are going to be second order. So that's really straightforward in the good regions. The challenge comes is when you try to do these do chains of RG steps. The bounds that you get have a tendency to get worse and worse, and the more steps you run, and so you need to have some outside control, some external control, if you will, that these flows don't get out of control. And so that required one of these steps, you know, where you say, what's the probability that something bad happens, and show that that's an exponentially small improbability event, and then that produces more bad regions. And so anyway, that's where the complications come in, is really maintaining this perturbation theory through, you know, in principle, infinitely many steps.
Okay, well, if there are no further questions.
I have one more question. Okay, so John, I've heard these kinds of semantic debates between people about the relation with Basco-Lane and Altschuler's proof, whether that was incorrect or incomplete, in the sense that, you know, yours is a non-perturbative proof, theirs was a proof to supposedly all orders in perturbation theory. So the non-perturbative effects that destabilize MBL in higher dimensions, should that have shown up in the BAA proof or at some very high order, or was it just, is it just fundamentally beyond what they did? Could you comment on how your results?
Yeah. Well, as I understand their work, I mean, their work isn't the easiest to understand either, but as I understand it, they were basically doing perturbation theory in the so-called forward approximation.
Yeah.
So anyway, yeah. So you're not going to see these avalanche effects in perturbation theory, and especially not in the forward approximation. I mean, just to get rid of the forward approximation involved me with rather complicated gymnastics in my proof, which I just alluded to a moment ago. Keeping this firm control over many scales is very non-trivial when you throw out the forward approximation.
Yeah, I mean, if I could comment there, I mean, I don't think BAA is all orders in perturbation theory, right? It's summing up some restricted classes of diagrams at all orders in perturbation theory, which is this forward scattering approximation. So like, not only does it not have the non-perturbative effects in it, but at least in principle, I could imagine there could be perturbative problems that don't show up in BAA because they're not in forward approximation.
Yeah, good. So then coming back to this wrong versus incomplete, I mean, it's certainly incomplete in that it only considers a limited set of processes, but I guess it would be wrong if it was claimed that it was a proof to all orders in perturbation theory, because it's not even that, right? If they claim to be that, then some of this would show up at some order, assuming it was truly taking into account all diagrams at all orders, right?
Yeah. I mean,
yeah, okay, yeah. Yeah, I guess the, in their defense, right? Some of these non-perturbative phenomena, like as theorists, we enjoy talking about them and coming up with universality classes and flow equations and everything. But the prospects for seeing them like in numerics or in experiments are rather dim. So the approximations they made are probably perfectly good ones as far as real world physics is concerned.
No, yes, I'm perfectly happy with that. It's just, what label should be attributed to their work? Is it a proof to all orders in perturbation theory? And I don't think it is, right?
Yeah, no, I agree with that. Yeah, it's okay. All orders within the forward approximation.
Yeah.
I mean, I would call it a perturbative argument, right? So.
Yeah, okay. I mean, I don't know if they really go to all, I mean, some of the subsequent works by Scardiccio and so forth, they did diagrammatics much more carefully, I guess, but that was also in the forward approximation. It pretty much confirmed what BAA was saying.
But I mean, if we call it an argument instead of a proof, I think there's no problem.
Yeah, okay. Yeah, I'm okay with that. I will say that, diagrammatically, like these non-forward diagrams are exactly the sort of things, when these walks, if you will, start to come back and back and back over and over again, that's really describing a situation where you get stuck in one of these bad regions.
Mm.
So at least heuristically, those are the kind of graphs. So it is important to understand how you go beyond the forward approximation.
Right. And just coming back to the Floquet question for a second, the central difference there is, of course, that now you can get resonances mod omega, where omega is the driving frequency. And that could, in principle, allow things that are off resonant to become resonant. And okay, the way out is often that, okay, if it is to become resonant, then maybe you have to act with the drive to some high order, which may rescue you. But you don't think your proof will be any more difficult in trying to do that, in trying to take all of that into account? Or maybe not any more difficult, but you think all of that should actually just go through just as the static case did?
Well, I guess, you'd have to plug in a version of the LLA assumption, which I guess would say, so, a slightly generalized notion of what it means to have a small denominator.
That's
small
right.
Denominator modulo the driving frequency. But other than that change, I haven't thought about it a great deal, but that probably would do it.
Okay.
All right. Any more questions? Okay, if not, let's thank John again.